Thank you very much. I'm typically not at all nervous about giving presentations, but today my wife is in the audience. So first I want to thank the organizers for inviting me to give this presentation. I also want to say how pleasurable it is to be back with many friends and colleagues. And it's a great meeting, and it's great to be back together in person. I also want to begin by acknowledging my collaborators in this project, Ala Humada, Mehmet Agaoglu, and Zanjin Kong, who contributed mightily to this project. Now, this meeting is about electronic imaging, and I think one of the great challenges of electronic imaging is that we need to bring together vision science and electronic imaging. And to my perspective, at any rate, electronic imaging and the devices on that side are all beautifully well-engineered, well-understood, governed by simple scientific rules. And on the other side, we have vision, which is this messy thing with very few laws or really well-established principles. So somehow we have to bring them together, and that's the challenge. And what I'm going to be talking about today is really a perspective or a way of looking at some of the basic aspects of early human vision that are important for electronic imaging and how we can see them in a nice, structural, systematic, and understandable way. So let's jump right in. First of all, let's think about what is the basis of early vision. It's variations in light over space, time, and color. Okay? It's not the absolute values, but it's the variations in light intensity. And those variations occur over different scales. You can have very fine details, you can have slow oscillations, and they're both important. And we can also think of those different scales as being different frequencies of modulation of the luminance over these dimensions. Now, it's been appreciated that sinusoidal variations are a nice systematic way of describing these various variations at different scales or frequencies. And so we've come to view the contrast sensitivity function as a fundamental entry point for human vision. Now here's a sinusoidal variation in luminance over space, and here's another one at a higher frequency, and here's a variation over time. And here's a variation over both space and time, producing a motion signal. Here's a variation of color over space, and here's a variation of color over both space and time. So those are the kind of signals that we're interested in, and if we put all those together, we can essentially create any image we want. Now, we'd like to know what is the sensitivity to these various modulations of luminance or color over space and time. And the way we measure that, of course, is using what we call a contrast sensitivity measurement, where we gradually reduce the contrast of a signal until it's just visible, and at that point, we call that contrast the threshold, and the inverse of that is the contrast sensitivity. Now, if we do that, we can do that in all these dimensions that I've discussed, and we'll see what we find. But before we do that, I want to introduce some notation that I'm going to try and use very consistently. We have temporal frequency in hertz. We have spatial frequency in cycles per degree. That's the number of oscillations per degree of visual angle. And then we have contrast sensitivity, which I'm going to express as a log to the base 10. That's S. And then we have luminance, which I'm also going to express in log units with that capital L. And retinal illuminance, which is the amount of light that actually gets to the retina, I'm going to express in log trolins. That, by the way, is the product of the luminance and the area of the pupil. And finally, we're going to be thinking about sensitivity as a function of distance from the point of fixation in the visual field. So we're going to use R to express degrees of angle relative to the point of fixation. Now, what I'm going to start with is some classic papers in vision and look at them in a new way and see what they reveal. So here's a paper from way back, 1958, De Lange from the Netherlands, and this is a paper about temporal temporal contrast sensitivity. And here's the data that he collected. And the vertical axis there, again, is that log sensitivity that I mentioned a moment ago. And the horizontal axis is temporal frequency in hertz. And these are classic temporal contrast sensitivity functions. And the different colored curves are for different adapting light levels. The one at the bottom is for an extremely dim light level. You can see over there on the right, expressed in log trolins. And then the other curves are for higher luminances. Now, I should mention the bottom one is probably scotopic vision, relying on the rods. I'm not going to be talking at all about scotopic vision today, so we're going to forget about that bottom curve. Oh, sorry, there's an example of the kind of signal that DeLonge used to make these measurements. And again, he'd reduced the amplitude of that modulation until it was barely visible. Now, what we're going to do is we're going to replot these data with one simple alteration. We're going to express the horizontal axis in linear frequency terms. And now we see that the different curves all appear to be approximately straight lines, at least at the higher frequencies. Not only that, but those straight lines, if you look at the dashed curves, those are fits of a particular model to the data. Those dashed lines all have the same slope. Okay? So sensitivity falls off with a constant rate as a function of frequency. And the spacing between those curves is, amazingly enough, a linear function of the adapting luminance. So up at the top, you'll see an equation there. That's our first equation. Sensitivity is a function of temporal frequency, and retinal illuminance is equal to a constant plus a linear function of the temporal frequency and a linear function of the log retinal illuminance. So that's pretty cool. But let's go one step further. Now we're going to look at spatial modulation. Again, a very old and classic paper from Van Ness and Baumann. And here's their data. And of course, they look quite similar to the temporal ones, except that the horizontal axis is now, of course, spatial frequency in cycles per degree on a log axis. And again, the different color curves are for different adapting luminances in log trolins. And if we do the same trick of, there's an example of the kind of stimuli they were using. If we do the same trick of expressing this as a function of linear frequency, we find again that the curves are approximately well fit by straight lines, and the straight lines have the same slope, and they're separated by a linear function of the log adapting retinal illuminance. Okay, and so there we have our second equation up the top, which expresses spatial frequency, retinal illuminance, and again, this seems pretty cool. Now, these are both for separate spatial dimensions and temporal dimensions. What if we put the two together? Well, here's a classic paper from John Robson, 1966, where he used signals that were sinusoidal in both space and time. And I may have there's an example of the kind of signal he was using. Now, on the left plot, what you see are spatial contrast sensitivity functions. The horizontal axis is spatial frequency, and the different color curves are for different temporal rates of modulation. On the right are the same data, but replotted where now the temporal frequency is on the horizontal axis, and the different colors are for different spatial frequencies. And these are our classic data that have kind of defined our understanding of the relationship between spatial and temporal frequency for many years. But now let's do our trick again and put it on linear axes. And now we see that the curves all appear to fall off at a constant rate. We already knew that from the previous data. But the separation between the curves, if you look at the ones on the left, the separation between the different colored curves is a linear function of the other variable. So on the left, the separation is a linear function of the temporal frequency. And on the right, it's a linear function of the spatial frequency. So that allows us to write this third equation up top, where sensitivity is equal to a constant plus a linear function of spatial frequency and temporal frequency. So now we can put these all together, but first I wanted to just give you a picture. We're now going to be looking at things in the spatio-temporal frequency domain. So what does that look like? If anyone suffers from photosensitive epilepsy, please look away. But what you see here are modulations where the temporal frequency is increasing to the right, and the spatial frequency is increasing up and down. And this is the kind of two-dimensional spatiotemporal frequency space that we're working in. These are all noise signals, but they have those frequency characteristics. All right, so now we're going to put all the stuff we've learned so far together into one equation where we have a function that says that the sensitivity to a particular spatial frequency, temporal frequency, and retinal illuminance is equal to a constant plus a linear function of the other three terms. Notice there are no interaction terms. There's just separable. So that's, again, pretty amazing. And if you now look at what that equation looks like as a surface in the two-dimensional space where the two axes on the bottom there are temporal frequency and spatial frequency, and the vertical axis is that sensitivity, that's what it looks like. That's why we call it the pyramid of visibility. For those of you who are not familiar with Fourier transforms, we have both positive and negative frequencies, but don't worry about it. You can just look at one quadrant, just look at the positive frequencies, and that would be that space that I showed you in the previous slide. Now, if we change the retinal illuminance, what happens? Well, remember, it's a linear function of the retinal illuminance. So the pyramid shrinks into the sands of the desert, if you will, and sensitivity declines linearly with the log of the retinal illuminance. That green diamond at the bottom is something that we call the window of visibility. And we talked about this many years ago before we talked about the pyramid. But that's the total range of spatial and temporal frequencies that are visible to the human observer at 100% contrast. And that's a very important piece of information. Now, what about if we change the contrast of the scene? What happens then? Well, this shows what happens to that window of visibility as the maximum contrast is reduced. So if you have a display which can only produce contrast of a certain amount, then your window will be that much smaller. Now, these are currently being expressed in terms of retinal illuminance, and most of us working in displays or imaging technology don't think in terms of retinal illuminance. We think in terms of luminance. So what's the relation between those two? As I said, the retinal illuminance is the product of the pupil area and the luminance. Now, a while back, we developed a formula for the way in which the pupil changes in response to adapting luminance. And I won't go into the details of that formula, but what it allows you to do is to make a plot over here on the left of luminance and retinal illuminance related to one another. And these are actually logs. But you can see that there's a very nice and tight relationship for this particular situation. So we can basically rearrange our terms in our equation, and we can now have a new equation which is expressed in terms of luminance instead of retinal illuminance, which is what we really need for display engineering. Now, now that we've put together this equation, we can actually derive some classic laws of vision science. So one law is what's called the Ferry-Porter law, and that basically says that temporal resolution, that is the fusion flicker frequency, the point beyond the frequency beyond which you can't see any variation, is linearly related to the log of the retinal illuminance. And that just falls right out of the equation. I won't go through these equations, but you just simple algebra leads you to the Ferry-Porter law from the pyramid of visibility formulation. So this is an old classic law, but we can actually invent some new laws. So here is what I call the Van Nessen-Baumann law. So it should be Bauma. And that says that spatial resolution is linearly related to the log of the retinal illuminance. And there's the equation, and these are some data from Van Nessen-Baumann where those diagonal sections are showing the relationship between retinal illuminance on the horizontal axis and the limit of visual resolution on the vertical axis. You notice there is a kink at the top, so this rule doesn't persist forever. At some point, light adaptation ceases to have an effect, and then this no longer works. Next law is what I call Kulikowski's law. And this is, if you take that pyramid, and remember the green area at the bottom is the window of visibility, and you now look at the coordinates of that window of visibility, and you look at how the boundaries of the window are straight lines that show a proportionality between spatial and temporal frequency. And what that means is that at a fixed contrast and a fixed sensitivity, there's a perfect reciprocity between spatial and temporal frequency. All right. And finally, you can easily compute the boundaries of the window visibility from the equations for the pyramid. Now, so far I've been talking about foveal vision, and one of the great things here is that we can extend this to other aspects of early vision. In particular, we can extend it to the peripheral visual field. Now, how do we do that? Because up to this point, we've been talking about frequencies that are presumably extending over a large area. But to measure how things vary with respect to position in the visual field, we need a local signal. And so what we do is we use these Gabor functions, which are nice local bursts of frequency. And we're actually using Gabor functions in which the number of cycles is constant. So as you go to higher frequencies, the total area of the function becomes smaller. This pointer doesn't seem to be working, but anyway. Now, on the right, you'll see some data from a classic experiment, the so-called ModelFest study, in which we have sensitivity to these Gabor functions as a function of frequency, all foveal. Okay, but I'll still need to use this to advance the slides, right?
Yeah, exactly.
Oh boy, this is complicated. I hope my wife isn't watching. That's cool. Oh, you're gonna. Anyway, over here you can see. This is not much brighter, is it? Anyway, you can see that for these data from that study, using these constant number of cycle Gabors, that again they show a linear relationship between sensitivity and spatial frequency. And so we can again use the pyramid of visibility model, albeit with slightly different parameters, to describe sensitivity as a function of these constant cycle Gabor functions. Now, I'm not going to bore you with lots of pictures of data from the literature, but we fit these data to a large number of studies, 8 studies, and in general, the model seems to work very well. And how do we modify the model to accommodate position in the visual field? It turns out to be a very simple modification. Right here, I can't see it, I don't know about you folks, but if you look at the expression that is multiplied by C sub f, remember that's the constant that says how sensitivity falls with spatial frequency. Instead of now multiplying that by frequency, there's another term in there. And it's basically changing the scale of the visual system. So frequencies are effectively being changed by a linear function of distance from the fovea. We call this a theory of local scale. It says that the processing is identical everywhere in the visual field except for a change of spatial scale. And this introduces one new parameter, that's C sub r, which describes the rate at which that scale changes with eccentricity. Now, if you look at that equation and you now plot some things, you can see the figures at the bottom. First, on the left, we have the contrast sensitivity function expressed as a function of spatial frequency in the traditional way, but for different eccentricities. So at the fovea, it's that blue curve, nice high sensitivity to high frequencies, but as you go to more eccentric locations, sensitivity falls off very rapidly. Likewise, you can plot a particular frequency and how its sensitivity varies with eccentricity. So a low frequency changes slowly with eccentricity, but a high frequency changes very rapidly. And you can express it again in terms of cycles, and then you get a more constant relationship. Now, we can take an image and essentially filter it with the pyramid of visibility as a function of eccentricity, and you get something like this. Again, here's where we're going to put our fixation point, and now we're going to do the filtering. And now things should be, again, in focus somewhere around here, but progressively blurrier as we go off to the margins. Of course, this is computed for a particular viewing distance, but you get the idea. Now, a number of years ago, there was a plenary talk at this meeting, and it was about the first photograph taken of a black hole. Some of you may remember that. And I was thinking to myself, how can I compete with that? Okay? And then I thought, well, that one was about outer space. You just have to show them something they've never seen about inner space. Okay? So I'm going to tell you now about something that I call the visual Umwelt. Some of you may be familiar with this term. German word meaning environment, but more generally is often taken to mean the kind of sensory environment in which we experience the world, and different species may have different Umwelt. So what I'm going to now show you is the visual Umwelt, and by that I mean I'm going to take visual noise and I'm going to filter it by the pyramid of visibility and do that appropriately for different eccentricities. And hold your breath. And here it is. Okay, so now right at the center, things should be quite in high resolution. This weird Gabor function here is a defect in the screen. But you should see this is 30-degree eccentricity horizontally and plus or minus 14 degrees vertically. So that's a picture of the Umwelt. All right, now, so far, everything I've been saying has been about luminance, about variations in luminance over space and time and eccentricity. What about color? Well, first of all, we have to go back and think about the fundamentals of what we know about early visual processing of color. And as it says here, visual signals consist of modulations over space, time, and color. And human vision is trichromatic, and it begins in the three classes of photoreceptors, which we'll call long, medium, and short. And here's a picture of the action spectra of those three classes of photoreceptors. But then the signal is rapidly transformed into three opponent channels, and there's some controversy about exactly what those channels look like, but roughly speaking, we think of them as being a white-black channel or an achromatic channel, and a red-green channel, and a yellow-blue channel. And so here's how that happens. Here are the three photoreceptors, and again, we take the difference between the red and the green, or the long and the medium wave photoreceptors to get the red-green channel, and the yellow-blue channel is the difference between the short wave and the sum of the medium and long, and the white-black is the sum of the medium and long. All right, so we have three opponent color channels. The pyramid of visibility, we extend that into the chromatic domain effectively by creating three pyramids: an achromatic pyramid, a red-green pyramid, and a yellow-blue pyramid. So first we need to talk about modulation and color and how to express that. So here's a signal, a Gabor function, but now we're modulating the color as well as possibly the luminance. And you can think about the background as having a base color and the modulation as being the base plus some modulation. So we can express that base color in terms of the excitation of the long, medium, and short wave photoreceptors. And the modulation is a delta from that point. And so we can think of the delta L, delta M, and delta S. And we can now take the contrast by separately normalizing those three channels. So it's the delta divided by the base color, or delta L over L, delta M over M, and delta S over S. Now that we're still in the trichromatic domain, to go into the opponent domain, we're going to multiply that contrast by a matrix, and we're currently using the famous matrix from Darrington, Krauskopf, and Lenny to transform those trichromatic signals into this modulation, which is now opponent. So it's a achromatic modulation, a red-green, and a yellow-blue. So that's the stimulus. How do we build the pyramid? Well, we basically just have the pyramid that you've seen previously, except that these terms, S, C0, CW, are now all vectors of length 3. Okay, there's a different sensitivity to temporal frequency and to spatial frequency in the luminance and chromatic channels. Effectively we have, as I said, there's our achromatic pyramid, there's our red-green pyramid, and there's our yellow-blue pyramid. And you'll notice that the red-green and the yellow-blue ones are, if you will, narrower, and that's because sensitivity to spatial and temporal modulation in the chromatic channels is lower than it is in the luminance channel. Now, if we wanted to compute the response to a particular modulation, like that chromatic Gabor function I showed you earlier, we just take that modulation signal that I defined a moment ago, and we multiply it by 10 to this s, and again, that's a vector of length 3, and we get a response, which is the response in the 3 channels, and then we can combine the 3 using a Minkowski sum, where we take their absolute values, raise it to some power, might be around 4, add them up, and then take the 1 over 4 root. And we assume that's going to be equal to 1 at threshold. That'll be 1 J and D. So this machinery that I've just described is a way of computing the sensitivity for an arbitrary modulation in color and space and time and eccentricity, and figuring out what the sensitivity should be to that signal. Now the question is, does it work? Okay, it's all very well to throw these equations up, but does it work? And I have to say, it's early days. Okay, we've harvested some legacy data from the literature, and so far so good. I'll show you a little bit in a moment, but I do have to admit that this is a work in progress. I sometimes hope that the work won't extend too long, but so far it's early days. In any case, here's one study, and this was the data from this study were kindly shared with us by some folks who are in the audience right now. But in this study, what they did was they looked at modulation in achromatic and 2 opponent color directions. And they looked at sensitivity to Gabor functions over a very wide range of luminance, going up to 10,000 nits. And they had a bunch of observers. And in these panels, the horizontal arrangement of the panels is the adapting luminance, and the 3 rows are for the different color directions of modulation. The red points are the data, and the blue points are the fit of the pyramid of visibility to those data. And I hope you'll agree that the fit is pretty darn good. One important thing to realize when looking at curves like this is that there are very few parameters that are all being jointly fit to all these data. We're not separately fitting the data to each one of these panels. It's all being fit together. Now, there are some failures of the model. You can see here at very high luminances, there's a departure there, and that probably has to do with like pigment bleaching or something of that kind. What about temporal modulation? Here's another study, and I think if I advance this again, you'll see an example of the kind of signal they were using down there, where they're modulating the color, and they use different adapting luminances. So the base color, this picture here is showing the position of the various base colors, and then they modulate it in different directions in color space from those base colors. And so in these panels here, the horizontal axis is the base color, and the vertical arrangement of the panels is the direction in which they modulated the signals in time, right? These are modulations in time now. And again, the red points are the, I guess here I actually did it the other way around. Sorry, the blue points are the data, and the red curve is the fit of the pyramid of visibility to these data. So again, I hope you'll agree that things are working reasonably well. Now, at this point, I'm going to switch and show you a few applications, but before I do that, I just want to summarize briefly what we've done. We've got a model for the contrast sensitivity function of both space and time that involves a very small number of parameters, and it also describes how that sensitivity varies with adapting luminance. We've then extended it into the peripheral visual field, and we've also extended it to chromatic modulations. So that's the complete package so far. Now, because I work at Apple, there's a limit to how much I can show you about applications, but I did think that I could give you a suggestion of the ways in which this could be used. And the first one I'm going to be talking about is about something called the screen door effect. And I think many of you are familiar with this, so here's a kind of a crude illustration. But if you have a display in which the resolution is perhaps a little bit too low, and in which the illuminated pixels don't individually fill the area of the pixel, so they have an aspect ratio that's too small, then you can get a visible grid superimposed on the image. And this is quite often the case for near-eye displays like AR and VR displays when, again, the resolution isn't really adequate. And it can be very annoying, and it can kind of take you out of the virtual space that you want the user to be in. So, important thing to appreciate about the screen door effect is that it's a periodic signal. Okay, it's completely repetitive and periodic signal. And so we can actually determine the frequencies that are involved in that signal by looking at the individual pixels and knowing, of course, the viewing distance. So here's an example of a pixel arrangement. This may be familiar to some of you, but this is actually what we call a macro pixel. So it's actually 2 pixels, but they alternate. This is the basic unit. So this is the periodic unit. And so what we can do is take this macro pixel, and we can compute the discrete Fourier transform of that, and that'll tell us what the amplitude is of the various frequencies in this arrangement. Now, if you think about it, the only frequencies you really care about here are the fundamental and the second harmonic, because any other frequencies are likely to be well above the limit of visibility. So we're really only concerned with a small array of frequencies. Then we can use the pyramid of visibility in combination with our knowledge about the peak luminance of the display and the pixels per degree, which is related to the viewing distance, and possibly any veiling luminance that might be present. And we can put that through the pyramid of visibility, and then we can pool, because there may be more than one frequency involved. There's horizontal frequencies, vertical frequencies, and there may be both the first and the second harmonic. And we can come up with a J&D for that screen door effect. And that, in turn, allows us to build nice little tools like this, where what we're doing is we're saying, well, all right, let's suppose we have this pixel arrangement, and let's suppose the viewing distance is such and such, and the peak luminance is such and such, and the veiling luminance is such and such. And these are the J&Ds of visible artifact that would result. And, of course, we can have a full white screen, which would produce a certain amount of J&Ds, or we can have a full red screen, or full green, or full blue. And as you'll see here, the worst case is actually the full red screen, for reasons that I could go into. Anyway, so this is very useful if you want to play around with your design parameters. We can also produce a plot like this, a slightly simplified representation, where here we're looking at the aperture ratio. That's the amount of the pixel that is actually illuminated, the amount of the pixel area that's illuminated. This is the pixels per degree, which again is going to be based on the pixel pitch and the viewing distance. And this color code here is actually log J&Ds. So 0 means 1 J&D. And you can see that curve is separating the good bits, the green parts, from the bad bits down there. And you can plot your particular system in this space and see whether it's going to have a problem with screen door effect. All right, next one I want to talk about is dynamic noise. So dynamic noise can arise from lots of sources. For example, the capture with a camera, and quantization, and dither, and compression, and just electrical noise in the display. And I'm talking here about dynamic noise. So to model the visibility of this dynamic noise, we have to take into account both the spatial and the temporal aspects of that noise. And that's where something like the pyramid can be very useful. So here's an example. This is just a made-up signal of some signal passing slowly across the display. And these noises are often signal dependent. So we need to build into our metric some way of taking into account the spatial and temporal distribution of the artifact as well. Here's what it might look like with some exaggerated noise superimposed on it. And again, what we're trying to do is quantify the visibility of that noise, and we're going to do it basically by comparing the original clean signal and the noisy signal.
I'm having some trouble with the connection.
Thank you.
Please try again.
So here's the difference between the original and the noisy signal, sort of what you might expect it to look like. I've superimposed it on a uniform background, but it's actually both positive and negative. And now we're going to filter that with the pyramid of visibility. And if we do that, what we get is what you see here. Whoops, I jumped 2 steps, but bear with me. That's the noise signal filtered by the pyramid of visibility. So it's correctly weighting the different spatial and temporal frequency components in that noise signal. And now we're going to pool that over space. So we're taking the energy of this signal, just taking the absolute value and squaring it, and pooling that over space over some aperture, because we think that the visual system will integrate that error signal over a certain area of space. And then finally, we do the same thing, but now we pool over time, and that looks like that. And again, we have some notion of how, over what interval of time, the visual system is going to integrate the visibility. And finally, we turn that into a J&D at the end of the pipeline. So this is an example of a noise visibility metric that we can build on top of the pyramid of visibility. All right, the last application that I want to mention is one that actually dates back to earlier work on the window visibility, but it actually was, it's much more powerful with the pyramid. So this has to do with motion artifacts from frame rates and how you present video. So here's a nice, relatively smooth video, and that's at 50 hertz. And if we present the same video at 10 hertz, of course, it's going to look jerky. And there are various ways we can ameliorate that by doing interpolation or frame averaging and so forth, but they all have penalties. So the key question is, how can we use the pyramid of visibility to evaluate a particular frame rate under a particular set of constraints? And again, to remind you, the window visibility is the base of the pyramid. So now if we expand it out over here, we have the spatial frequency axis horizontally and the temporal frequency vertically. And you can only see stuff that's inside that diamond. So now let's take a slightly simpler signal, just this vertical line over here on the left. And if we look at that as a space-time map, we see here is space. Well, it's not moving, so it's only at position 0. And it's at that same position at all points in time. So the vertical axis is time. This is the Fourier transform of that. Now we have spatial frequency, and because it's a nice sharp line, it has frequencies extending over both positive and negative frequencies, but it's all at 0 hertz because it's stationary. And that green thing is the outline of the window of visibility, so the only portion of the signal we see is the portion within that window. Now, here's what it looks like if the line moves. Sorry, I have to advance this. That's what the space-time image looks like. It's now a diagonal line. The position is a function of time. And the Fourier transform is also a diagonal line, and it's also oblique. And you can now see the portion of that line that fits within the window of visibility. Now the key question is what happens when we sample at a particular frame rate. And so this is actually 24 frames per second. And now the line is only being presented at these discrete points in space and time, as shown in the left plot. And that replicates the spectrum. And so now the window includes both the original spectrum, which is good, but it also includes 2 replicas, there and there, which are within the window and will produce unattractive artifacts, which would generally manifest as what we call judder, which is jerky motion. So, of course, the simplest way to get rid of that is just to increase the frame rate and move those replicas outside the window. The replicas are at intervals of the frame rate. So this is a very simple case. But if you're interested, I have a paper in which I go through an enormous range of different manipulations that video can be subject to, both at the capture end and at the display end, and how they're all manifest in this frequency space. and how they can be handled by the pyramid of visibility and the window visibility. I had to turn this plot on its side to fit it into the slide, but if you're interested, you can go to this paper and read all about it. But the kind of artifacts that you can model are things like motion blur, strobing, which is where you see multiple copies of an object, also sometimes called the phantom array, and motion judder, which is unsmooth motion. And the kind of controls you can think about and what their effect is are things like obviously the frame rate, but also the optical blur at the camera, the shutter angle, which is the amount of time you leave the shutter open when you're capturing the image, persistence, the amount of time you expose each frame at the display end, whether you repeat each frame, as they do in film, 3 times, and whether you do any interpolation amongst the frames. And all these things can be handled within this scenario. I should also mention that although I can't tell you a lot about my own work in this area, there is a recent paper in which they've basically exploited these ideas to full strength, and so you can go take a look at their paper and see how they have used these ideas. All right. I'd like to wrap it up at this point and just kind of remind you of where we've been, what we've done. We have this tool, and these are some of the applications that it can be applied to. I've talked about some of these, but there are many others as well. Things like the image and video compression and foveation and flicker and what resolution you need to display. And basically the pyramid of visibility is trying to capture these dimensions of space, time, peripheral vision, color, and to do that all within the context of light adaptation. And to do it in a simple, structured way that can be easily applied to engineering problems. And with that, I think I'll stop. Thank you very much.